Now let's come back and let's start to discuss locality sensitive hashing or LSH. Right. So I do like this kind of names. I mean, high dimensional similarity search. So we can discuss similarity search first, then see how it goes on high dimension. Locality sensitive hashing. Let's look at hashing first, and then we discuss why it is necessary to make the hashing locality sensitive. Well, we all know hashing function or the how hash works, or at least I mean you must have used a hash map before, right? So basically, this hashing is a two-phase procedure. We have a index and retrieval. For the index, we map the data or objects to values. Right. So the values here is the hash key. All right. And for the retrieval, we want to retrieve identical objects. So the idea here is for same data, they must have same hash key because the function is deterministic. Okay, so the function takes the same data, must generates or produce the same hash key. And for different data, we want them to have different hash keys. Well, we cannot guarantee this because no matter how you design your hash function, it is always possible that you would have generated same hash key for different data, but with a strong enough hash function, we actually can guarantee this with a high probability. Or say in most cases, different data would have different hash keys. Then in the retrieval phase, or when the query comes, we compute. Let's say here we should use H is better. Anyway, we compute the hash key of the query, right? And then we search this hash key within the hash map. And then we know whether we have the same object in the database or not. Right. Or we can, for example, in hash map, these are the keys, and we can change the values. Depends on our application. For example, if we do a word count, the key is the hash value key, the hash value of the query. So for the value in the hash map, we can add 1 on it as we count one more word. Right. And also the hash join has been widely used in database systems. Right, when we do the join. Right. So the idea is just as simple as this. The good thing about hashing is that the cost is low. By cost is low, we usually discuss from two perspectives. One is space and one is time. So for the space cost of a hashing algorithm, the space cost would be the big O of n, because for each object, you would have compute a hash value of that object, and you store this hash value. Okay, so for n objects, you would store n hash values. And for the time, we usually discussing the query time. or the retrieval time. So for a hash algorithm, when we do the retrieval, when the query comes, we compute the hash value of the query, and then we can directly access that hash key on the hash map, or access the value of that hash key on the hash map, because we can directly link the hash value to its address in memory. All right. So the time cost of a hash algorithm is usually O1. It's constant. Yeah, constant time. All right. And even for the construction time of a hash algorithm would be big O of n, just like the space cost. All right. Now, the hashing algorithm looks very good. It is easy, and the cost is quite low. So why we cannot use it in nearest neighbor search, or what prevents us from using the hashing idea in nearest neighbor search, right? So the problem here is that even a minor difference leads to a totally different hash keys. And this difference, okay, how to, all right, let's say apparently different data would have different hash key. Moreover, the difference between hash keys, so say H01 and H02, the distance between hash keys has nothing to do the distance between the objects. There's no relationship between these two. Okay, so when even the objects are really close to each other, their hash key could be totally different, could be quite different from each other. Right. So that's the reason why we cannot directly use this hashing idea in nearest neighbor search, because we're not aimed at finding exactly the same objects, right? Okay, now let's look at the other part of LSH, which is locality sensitive. So with locality sensitive, it is possible that we can use it in nearest neighbor search. All right, so the idea is we want to make the hash functions error tolerant. So in this case, for similar data, we want them to have same hash key. And for dissimilar data, we want them to have different hash key. Previously, here is the same data and different data, but here is similar data or dissimilar data. And the probability is also different, because we cannot 100% guarantee similar data to have same hash key. So we do want that both of these two scenarios with high probability. Okay, so here is a 100% probability. It no longer exists. All right. Now in the retrieval part, assume that we have this kind of index where similar data have same hash key and dissimilar data have different hash keys. Then in retrieval phase, we compute the hash key for the query, of course. We obtain all the data has the same key with query, because this data supposed to be the similar data. The data that is similar to the query, right? we call them candidates. All right, we call them candidates. Then we find the nearest one to the query from the candidates. So this is this procedure, this querying procedure is a classic. It's called a candidate generation. This is the first step, and the second step is verification. So generate the candidates, or obtain the candidates, and verify the candidates to compute the nearest one. In this case, what is the cost? For the space cost, it is the same because the index structure does not change. Right? We just change the hash functions. And for the time cost, besides of that O1 here is the same. We need to do the verification. Then we need a big O of the candidate size. Right. But since the candidates usually not too many, or at least it is just a small portion of the whole data set. So this is still much better, much better than big O of n. So that is the advantage of LSH. Right? We no longer need to linearly scan the whole data set. All right. But see, the idea is good, or the wish is good, but it is not the real LSH. Right? We still have several unsolved issues. And in this lecture, we're going to go through these unsolved issues. I mean, it has been solved, just unsolved till now. All right. We will see how we deal with them. So first of all, definitely would be the LSH functions. So what are functions that can satisfy this kind of condition, right? For similar data have same hash key. For dissimilar data have different hash keys. Now we first give a formal definition of the LSH function that we aim to have, or what we need. All right. So basically, given points O1 and O2, because we're talking about similarity or distance, that always involves two parts. So point O1 and O2, distance R1 and R2, you can take them as let's say R1 is for those similar ones, R2 is for those dissimilar. Yeah, dissimilar ones. Right. And probability of P1 and P2. Now, an LSH function should satisfy, let's say, first of all, similar data should have same hash key with high probability. Right. So if O1 and O2, the distance are smaller or equals to R1, so they are similar, right? That's why their distance are close to the distance are small. Then the probability of they're having the same hash key is large with a high probability. So we want P1 to be high. All right. And second condition, for this similar data, we want them to have different hash keys with high probability. Now for this similar data, we define them as the distance larger than R2. Right, so apparently here, R1 should smaller than R2. Right? Otherwise, it is meaningless. Right? So if we have for this O1, O2, the probability of their hashing values are the same, should be smaller than than P2, which means the probability of different is larger than, so the probability of, say, the probability of HO1 not equal to HO2 is larger than 1 minus P2. 1 minus P2 should be a large number, right? A high probability. In this case, we want P2 to be small. Right. So in general, we do have here we do have R1 smaller than R2 and P1 larger than P2. Now, this is all we need. Okay, this is all we need. You don't really need to memorize this this formulation or definition. You just memorize or try to understand. Try to understand from the very beginning of the original hash function. We have same data and different data. How do we going to organize them? And for LSH, we have similar data and dissimilar data, right? And here we just give it a mathematic formulation, right? That's it. Now, the next question would naturally be, what is this H if we have a given a fixed distance or similarity function, right? So we will discuss three commonly used distance function and their corresponding LSH function. Right. So these are Jaccard similarity, angular distance, which is the angle between two vectors, and Euclidean distance. Right. All right, so let's start from Jaccard similarity, where the LSH function or the hashing schema is also called a min hash. So when we discuss about Jaccard similarity, where Jaccard similarity is about the set, okay, the input is a set. So each data object is a set. So, and then the Jaccard similarity between two sets is their intersection divided by their union. Their intersection size divided by their union size, right? So if we draw a Venn graph, it should be this part, the red part, divided by this whole blue part. All right. Now the LSH function for Jaccard similarity, we randomly generate a global order of permutations for all the elements in the union of all the sets in the data set. All right, so that's why we have Yes, here should be S. That's why we have the union from S1 to Sn. And then we let the HS, the LSH function of S, be the minimum member of S with respect to the global order. Right? If we just say it like this, it's a little bit dry. So let's use an example here. For example, these are the elements in S. It's a set, okay? And we use the inverse alphabet order. So from Z, Y to B, A. So it's inverse alphabet order. And then we reorder S. We have I, H, E, C, B. We take the minimum member of S within this reordered one, right? Which is I. I is the first member. So the minimum member could also, you can think it as the first member, right? Therefore, then the HS is equal to 1. Equal to I. Okay. So now we compute the probability of HS1 equals to HS2. Now we only consider the elements in the union of S1 and S2. Okay, we don't consider other elements because either HS1 or HS2 they must the value must in S1 union S2. Okay, in the union of these two sets. So we only consider the elements within these sets. These elements is the possible values of possible hash values of S1 and S2. All right. Now for every element, it has equal chance to be the first element among S1 union S2 after this reordering. All right. Here, due to the time limitation, the proof here, as well as the proof of the next two hash functions, and also we probably got a little bit more complicated formulas or mathematics within this week and the following weeks. If you cannot understand, it is okay for you to skip this for this course. This is not the core part of this course or of this this LSH part. It is not as important as the LSH schema. So here I just want to show you how it works from the very beginning. All right. So it is okay for you to memorize it without understanding it. But if you are really interesting, you can first of all think by yourself. You can find proofs online, and you can also, definitely ask questions on Piazza. But I do hope you did your own research before that. But still, any question is welcome in the Piazza. But we probably don't ask such questions in the for the online consultation. All right, because not every team member is is familiar with all the details here. This proof is not so relevant to the purpose of this course. So for the online consultation, we kind of want to reserve the time for more valuable questions. All right. Okay, now let's comes back to the slides here. So every element has equal chance to be the first element. All right, then there comes two scenarios or two situations. One is that E is in the intersection of S1 and S2. Okay, so in this case, because E is the first element, then HS1 should equal to HS2. Because either of them, since E is the first element in the union of S1 and S2, it must also be the first element in S1 and S2. All right. In this case, these two will be the same. This is the only if part. For the if part, if HS1 equals to HS2, then we know that actually here we should add E to be here. Then we know that E is in S1 and E is in S2. Therefore, E is in the intersection of S1 and S2. All right, now if E is not in S1, the intersection of S1 and S2, right? Let's assume that E is in S1 without loss of generality. Right? We assume that E is in S1 and not in S2. Right? In this case, since E is in S1, then HS1 should equals to E, and HS2 must not equals to E because E is not in S2. Right? This is the only if. Yeah, we have to do this if before. So for the if part, if we say HS1 not equal to HS2, and we know that one of them equals to E, again, let's assume that HS1 equals to E. Then E is then E is in S1, and since E is the first element among the union of S1 and S2, and HS2 does not equals to E, means E is not in S2. So this is the if part. All right. Given these two conditions, now we can look at the probability of HS1 equals to HS2, which should equals to, here this part is the total elements in S1 and S2, in the union, of S1 and S2. And here is those EI makes HI, for HI, means we use EI as the first elements. Right. So the divider, this part is those EI that has the HI of S1 equals to HI of S2. Now, since we have know that HI of S1 and S2 are equal, only if and only if E is in S1, the intersection of S1 and S2. So here, this part is the size of the S1, the intersection of S1 and S2, and this is the, as we have mentioned before. So this part again is the Jaccard similarity. All right. So this is so now we have proved that the probability of they have the same hash value equals to their Jaccard similarity. then you can consider for the similar data, the Descartes similarity is high. Then they are more likely to have same hash key because the probability of they have same hash key is higher. And for dissimilar data, the Descartes similarity is low, then the probability of having the same hash key is low, so have different hash key is high. So it's this is for mean hash. This is for mean hash. Now let's look at LHH function for cosine similarity or angular distance. Now each data object is a d-dimensional vector. Okay, it's no longer a set because we're talking about the angular distance is the angle between two vectors. Right. So the data object is a d-dimensional vector, and we use a theta of x and y to represent the angle between x and y. Now the LHH for angular distance, we firstly randomly generate a normal vector A, where each element in A follows a standard normal distribution. Okay. Then we define the h of x, A is the hyperparameter, equals to, this is a sine function, which is defined here. The sine function of A transport times, dot x. All right. So here the sine function, if the input is larger or equals to 0, then the sine function returns 1, and if it is smaller than 0, means it is negative, then sine function returns minus 1. Okay, so the hash value of same hash, right? The hash value would be either 1 or minus 1. So it's a binary case. Now the meaning of this hash value is actually see x lies on which side of A. So here should be A. Sorry. Yeah. So this is A, and A transport dot x is positive when the point x lies on the same direction of A, right? And it is negative otherwise. So as you can see here, these points on the right side of no, sorry, it's on the same side of A, which is the hash value is 1, and for these parts, these points, the hash value is minus 1. So why this same hash? It looks really simple, or at least simpler than mean hash. Why it works, right? So let's again compute the probability of O1 and O2 have the same hash value. Right. So we know that O1 and O2 are different if and only if they are on different sides of A. Here, to be precise, it actually should be on the side of the hyperplane that's using A as its normal vector. All right. So anyway, let's look at the example here. This is O1, O2. This is theta. So for this hyperplane, O1 and O2 are on the same side, so the hash function would be the same. And also for this one and this one, you can try. Sorry, it should across the origin point, but you can try different hyperplanes, and only when the hyperplane across this blue area, it divides O1 and O2 on the different sides, and then the hash value would be different. The hash value would be different. So compared with all the possible hyperplanes with regarding to this circle here, so this is pi here, we only care about the blue area where the hyperplane touches or across the blue area when HO1 not equal to HO2. So this blue area, the ratio between this part and the whole part would be theta versus pi. Right. So this is the probability of HO1 not equal to HO2. Then the probability of HO1 equals to HO2 is 1 minus theta over pi. Now if we look back, remember it's 1 minus theta over pi. For similar data, the theta is small, right? The theta is small, so theta minus theta over pi is small. 1 minus theta over pi is large. So it will have a high probability to share the same hash key. And so you can do the rest for the dissimilar data. And this is for same hash. All right. And for the last part, let's look at the LSH function for Euclidean distance, which it is called a p-stable LSH. So now, each data object is a d-dimensional vector, and the distance function we're using here is the Euclidean distance function, where xi and yi are the ith element of x and y. Now, similar to what we have been doing before, we randomly generate a normal vector A, where each element of A is identically sorry, not identically, independently distributed in a normal distribution, a standard normal distribution. All right. So we know that the normal distribution is too stable. This is the major property that makes this whole thing works. So too stable means given AI is follows the standard normal distribution, then this part is actually A transport X follows the normal distribution of a mean of is 0 and variance is the norm of X to the power of 2. Right. Okay. So with this property, we define the hash function for Euclidean distance, the p-stable LSH function. AB is the hyperparameter. So the hash function would be the A transport X plus B divided by W, and take a floor function. So B follows the uniform distribution between 0 and 1, and W is user specified parameter. So let's see, if we compute the probability of O1 and O2 have the same hash value, then here is the formula. All right. And the explanation is here. We won't explain this in this course, as I have explained before. It is not the essential part of this course. But if you are interested, you can search for the original paper or search for the tutorials on the internet to understand why it is formulated as this. But we'd rather look at the intuition of this whole p-stable LHH thing. The idea here is that, all right, similar points have a higher chance to be hashed together. How do we do this? Let's consider this is A, and these points are the original points, the data points. All right, and these 4 points we call it projection, or it's actually a transport X plus B. No, divided by a W. Yeah, just this part. All right. So the blue lines here are actually the idea of why we divide it by W, and also then with the floor function that makes, say, the blue point and the purple point would have the same hash value as they lies in one partition, or we call it a bucket, because their projection was in the same bucket, so they would have the same hash value. So for all the points that their projection, which is A transport X plus B, lies in the same bucket, or in this same partition, or the same trunk, same trunk or partition, they're all the same. Anyway, they would have the same hash value, okay? And for those lies in different buckets, for example, the black one here and the green one, they will have different hash values. Now, why we say similar points have higher chance to be hashed together, let's consider 2 points that are close to each other. And let's consider because the only thing that would affect, B's effect is not that obvious. Obviously, it's more like existing for the purpose of the proving thing. So A is more important. It determines how this the projection of these points, how they will be organized. So if this is the A, then this would be I mean, it's not exactly like this, but similar to this. This would be the projections. All right, if let's try another A. Say if this is the A, then this would be the projections. So you can see that in the worst case, the projection is like this, and these are their projections. So the maximum distance of their projections is basically the same as their distance. The distance between these 2 points. Okay. And as you may also notice, if you try different A, the different projection vectors, in the most case, for example, like this or like this, their projections will not be far away from each other too much. But if we consider 2 points that are far away from each other, and we consider different projections, then in most cases, right, their projections would be far away from each other. Only when the projection is like this, they would have the chance to have similar to have their projections close to each other. Now, apparently, compared to the example here, these two pairs, these 2 points would have a lower chance to be hashed together, because their projections would be usually far away. If we say if we define W is like this much, right? So they will have very little chance to be hashed together. Now, if you do the math here, you can compute it by yourself, but gladly, actually, I have done it for you. So this is the probability of x and y has the same hash value with for different hash functions with their different similarities or the distance. So this is well, the y-axis is always the probability. This is the Jaccard similarity. This is the angular similarity, and this is the angular distance. And this is the L2 similarity. L2 distance. All right. As you can see, it is quite straightforward, because this is a 1 minus theta pi. This is no, the probability is just the Jaccard. It is just the Jaccard of x and y. Okay, and for p stable, here is actually it's actually computed as this. So for this case, we use w equals to 1, and we have the curve like this. So basically, when the distance is small, the probability is kind of high, and when the distance becomes larger and larger, the probability is approaching 0, right? So that is the probability for different hash functions. Now, as you can see, well, this kind of single hash function with this probability plotted like this, there are some problems. The main problem is that it is hard to distinguish if 2 pairs have distances close to each other. Well, remember, this is what we want to have. And now if we have 2 pairs, so in this case, we have pair 1 and pair 2. their corresponding distance is close to each other. It's close. And the probability of being hashed together is also close. So the thing is that it is too smooth, let's say. We don't want it to be too smooth because ideally we want that even this R1 and R2 are close to each other, are not distinguished too much. We still want to have P1 and P2 that are distinguished from each other. Or let's say we want somehow a figure like this. Of course, this is for similarity. So we want this point to be, we want here to be R2, and we want here to be R1. But the corresponding P2 is 0, and this P1 is quite close to this P2. So this P1 is quite close to 1. But let's look at, for example, the T-card is also the similarity. If we have R1 and R2, and this P1 and P2 here, then you can see the difference. You can see the difference. So that's what we want to do. I mean, even two pairs have distances close to each other. We still want to distinguish them. And furthermore, we want to control where the drastic change happens, the drastic change of this curve. For example, we want here this R1 to be close to the distance between O star and Q. Or this R1 to be like the given range if we do a range search. So the first issue of LSH is to find a LSH function, a single hash function, as now we have them. Here comes the second problem, is to somehow make the curve from this to be something like this, or this. Or this. All right? And in order to do that, it's actually the creator of LSH algorithm actually use this called and/or composition. So I will probably have to stop here for today. So let's take this as a homework or whatever for you to think. How do you use? So the idea is the general the high level idea is to somehow combine different hash functions together to have a new hash function or new super hash function that has better that can better distinguish two pairs in such case, or have this better curve that we want. All right. And yeah, that's pretty much for today's lecture. And I know some of you are concerned about the project. So the project is to use MapReduce to implement a advanced algorithm based on LSH. So in week 3, I will have to finish LSH and the algorithm called C2LSH. You are required to use MapReduce to implement C2LSH efficiently. Okay. So we will test your the efficiency of your implementation, and we also would have a bonus part for those efficient implementations. The top 20 most efficient implementations would get the bonus part. All right. So I will try to release project 1 within this definitely before Wednesday. All right. And also we would release a lab which is related to LSH, and hopefully can give you some idea of project 1. All right. So that's pretty much for today. I will see you on Wednesday.